Okay. It gives me great pleasure to invite Professor Gautam Bhattacharya to give this popular talk on the Higgs boson, on history of the Higgs boson. So for the few master students and undergraduate students I see who don't know Gautam, Gautam did his PhD from Calcutta University. And in fact, so he's a phenomenologist. A phenomenologist is a person who takes a theory of particle physics and tries to extract some information or predictive content which can then be compared to the data in any experimental lab. And Gautam actually worked at CERN in Geneva, where this Higgs boson was discovered in 2012. So it gives me great pleasure to invite him to talk about the Higgs boson. And thanks to the TAP invitees for coming to this talk as well. So Gautam, start.
Okay, thank you, Indu. It's working, no? Yeah, okay. So it's a great honor for me to have got this invitation. I don't get many invitation these days, so I welcomed it. uh, but I must say, on a sad note, this is the first time I'm giving a talk without Rajaji sitting on the front row with a reassuring smile. I mean, is someone, I wrote our Rajaji, it didn't belong only to IMSC, belong to the community. I mean, we all called him Rajaji with love, with respect, with as a leading light in our community. So, well, we'll miss him. I mean, we'll miss Rajaji's presence here. Now, it will not be that much of physics that I'm going to tell you. So, I have a few slides, but it will be better if you rather listen to me than look at my slides. So, it will be more like in the spirit of storytelling rather than giving you, physics insights. I mean, because 99% are probably from this conference who know much more than I do. I'm little out of contact with modern status of Higgs physics, which I got to know from Kajuri today, and a few more talks by some of the younger community members. Uh, you see that I'll take you back to 1920s, 1930s, 100 years ago, and I'll show you some of the faces you probably would definitely identify as your known faces from from many books or some other references. You can see it's a Solvay Congress. You can see Heisenberg, uh, Jordan, Max Born, Lisa Meitner, Planck. You can see Oppenheimer here. This is Meghnad Saha. Somewhere this is Homi Bhabha, Niels Bohr. I'll take you to what was happening in those days. So it's not out of place to show you this photograph. Uh, well, 100 years ago, uh, Maxwell's electromagnetism, which was a description of light as electromagnetic waves, special theory of relativity, which told us that mass is equivalent to energy, and quantum mechanics, which explained the stability of the atoms and a quantitative description of the atomic spectra. It worked very, very well. Now, Dirac equation, which according to Dirac was smarter than Dirac himself, for many reasons that I am not going to, many of us know that, the equations sort of presided over, it solemnized the marriage of quantum mechanics with special relativity. Now, out of these three pillars, namely quantum mechanics, special relativity and Maxwell's electromagnetism, on the basis of these pillars, in the early 1930s, the quantum electrodynamics was developed. Now, in quantum electrodynamics, the vacuum is not empty. Well, I'll come to that. and an experimental proof of the description of why and how vacuum is not empty. I will mention about it. It is full of, I mean, sort of transient ephemeral particle antiparticle pair that are momentarily created and destroyed, because for a very short interval delta t, according to uncertainty principle, the energy momentum need not be conserved. I mean, so caching that hypothesis, you it turned out that in quantum electrodynamics, uh, there is a problem, and I am going to tell you about that problem, the problem about the vacuum. And do not ignore the power inside the atom. As you can see that the binding energy is in a hydrogen is what, 13.6 electron volt, which means that within 10 to the 10 meter you have a potential difference of 10 to the 10 volt, well, I mean, of 10 volt, right. So, it is like a gradient of 10 to the 11 volt per meter. Compare that with an accelerator which is 10 to the 7 volt per meter, and like here in my watch you have a in your watch you have a battery which is like 1 volt separated by maybe a few millimeter, which is like 10 to the 3 volt per meter. So, you see that it is very important to probe inside the atom, because there is a high gradient of potential, and we will see the power of the vacuum. Okay. Now, in 1929, Wolfgang Pauli, a leading physicist in Zurich, got a remarkable postdoc from US. Well, those are the days when people used to go to Europe to do, cutting edge research. So, this guy was extremely smart, very intelligent, very fast in the calculation, but sometimes prone to making mistakes, but still, I mean, a remarkable postdoc. His name was James Robert Oppenheimer. Pauli told him, he was a research assistant of Pauli. So, Pauli told him, you calculate hydrogen spectra not using Dirac equation, using quantum field theory. Okay. Now, Oppenheimer's calculation had to take into account that an electron comes and it emits momentarily a photon and it reabsorbs it, and it can happen in many different ways. The intermediate photon can also split two electrons and they will recombine, all sorts of combinations they had to take into account. So, in 1929-30, Pauli and Oppenheimer were doing that calculation and they expected the result to converge. To their dismay, it diverged. The result was infinity, because they had to take into account all possible combination, all possibilities, and at the end of the day, the sum turned out to be infinity. That was in 1929-30. Well, I mean, 18 years later, in 1947, and a world war later, in 1947, in a conference which is a shelter island near New York, Oppenheimer convened that conference. I mean, he was chairing a session, he was the organizer. Now, this conference was very important. It turned out to be one of the most influential conferences of this century for many reasons. First, in that conference, it was established that particle physics requires language, and that was proved to be quantum field theory. Without quantum field theory, you cannot describe particle physics. Before that, I mean, it was not so very clear. I mean, you need a prescription and a formalism, and that was quantum field theory. That is number one. Then that was a conference where after many years, maybe 7-8 years, physicists were meeting without someone peeping on their backs. Is it classified? I mean, before that, I mean, there was a lot of, around during the war, you could not meet. I mean, there was a lot of embargo. They couldn't meet and talk freely about science. And this is after, of course, the Manhattan Project, the bomb was dropped and all these things. So, in 1947 Shelter Island Conference, the German physicists and American physicists and those Germans who were in Britain, who took shelter after the war, Churchill famously said that, I mean, we will win the war because our Germans are better than their Germans. So they are all meeting in Shelter Island Conference. And another thing that sort of shifted the center of gravity of modern physics from Europe to US. That was the beginning of the American story, Shelter Island Conference. One of Oppenheimer's students, Oppenheimer was a theoretical physicist, and his student, of course, started his PhD in theory during the war. The student got involved into Manhattan Project. His name was Willis Lamb. Using the technology of microwave reader that he developed during the war, Lamb measured a splitting of, between two lines or in hydrogen spectrum, which is 1 part in a million, okay, which according to Dirac equation, those two lines should have coincided, but he measured a splitting, and that was 1 part in a million, and he reported that in the opening session of that conference. That was Lamb shift. In the same conference, Isidore Rabi, who already got Nobel Prize for his discovery of nuclear magnetic resonance. He was an expert of anything related to magnetism, related to atomic and nuclear spectra eventually. So, he got it in 1944, got Nobel Prize in 1944 for NMR discovery. So, he came with a report of a measurement of the Landé G factor G in excess of 2 by 1 part in 10 to the minus 3, in 10 to the 3, so 10 to the minus 3, but non-zero, 0.1%. Now, you have to explain it. So, there were physicists like John Wheeler, then Swinger, Feynman, young physicists like Swinger, Feynman, and Feynman supervisor John Wheeler was there. Swinger's supervisor was Rabi, he was there. Hans Bethe was there. So, there were a battery of the top notch figures in theoretical physics and experimental physics present in that conference. So, Oppenheimer gave a task, he was a taskmaster, he gave a task, you have to calculate this Lamb shift in using the language of quantum field theory, and infinity which he got, well, some calculation he tried to get, would not be accepted as an answer. Neither 0 or infinity would be accepted as an answer. So, that was the task. So, Bethe did the calculation, well, and Swinger and Feynman were also doing the calculation. So, they found some non-zero, I am coming to that, and Swinger also calculated, his supervisor measured G minus 2. So, he calculated G minus 2 also. So, what came out is a remarkable story. So, they found that why they were getting infinity, they were, I mean, they were calculating all sorts of possibilities, like the electron emitting a photon and reabsorbing lights, like a snake eating its own tail, and that way getting infinite amount of energy because of all sorts of possibilities leading to infinite amount of energy attributed to the electron, and the electron energy is equivalent to mass. So, the mass was shooting up to infinity. So, what they found that you need a reference point, okay, with respect to that reference point, how different is the other thing. So, electron mass was a God gifted quantity. I mean, somebody has measured electrons mass, and that is finite. Okay, somebody has measured electric charge, and that is also finite. So, they found that the infinities that are coming to the calculation of the mass and the electric charge are very similar in analytic expression to the infinity that is coming in the measurement of the Lamb shift, in the theoretical calculation of the Lamb shift, all were infinity. So, if you assume the experimental value of electric charge and electron mass as the quantities that somebody had given you, and with respect to which you put the experimental numbers. So, replace the theoretical expression in terms of the experimental numbers, and in terms of those experimental numbers you try to calculate Lamb shift and G minus 2. all came out to be perfectly sensible. I mean, this is very simply I put it, but the whole thing about using a reference point of some experimental quantity, experimentally measured quantity to calculate something else was technically known as renormalization. So, quantum electrodynamics turned out to be a respectable theory at that time because of Feynman and Schwinger. They did the calculation in completely different ways. Schwinger did it was kind of the old Sommerfeld school of training, that you do the calculation pedagogically step by step, pages after pages, and finally come up with a number. Feynman used some trick which nobody believed. People said he's a magician, he's a cheat. So, but at the end of the day the results were matching. So, in that conference they made it to that things worked perfectly well. So, Tomonaga did it independently. So, Feynman, Schwinger, Tomonaga, they were credited with the discovery of this renormalization prescription and putting QED on a respectable platform, for which all got Nobel Prize. What is QED? Quantum electrodynamics, it's a gauge theory, which means gauge means phase. So, the thing should be invariant under some your equation should be invariant, Dirac equation should be invariant under the phase transformation with the phase of the electron. For example, you put a phase transformation of the electron, and if the phase is a constant, then of course Dirac equation is invariant. But if the phase varies at different point in space and in different instant in time, then of course the equation is not invariant. Okay. Now, if you want your system to be invariant under the transformation, you have to do something else. Just to give you an example, consider a circle. Okay, a circle. Now, if you rotate each point on that circle by the same angle, the circle remains a circle, right? But if you rotate different points of the circle by different angle, then of course the circle is deformed. Then if you want the circle to remain a circle, you have to do something else. You have to introduce some other force to counter what was that deformation at each point, right. So, what happens if your phase on the electron is different in different point in space and time, then what you have to introduce is what is called the gauge field, which is the photon, which is like a fabric it's like elastic fabric that stretches everywhere, okay, and its role is to correct for the deformation. So, something you deform just because of the transformation, and the photon or the gauge field will have to adjust itself, will have to transform itself accordingly, so that things remain exactly like before. So, the basic principle, the gauge principle necessitates the emergence of this force of the photon. So, it's an emergent thing, and it has to be necessarily massless. Without that, you cannot explain the invariance of the system. Okay. So, photon is coming out naturally, it is a massless photon. Okay. So, that is what they were and that is an important criteria, this masslessness, in order that you can calculate those parameters like G minus 2 or Lamb shift precisely to the satisfaction of the experimental results and theoretically consistent way. So, masslessness is a very important criteria for that. Okay. Now, during the 1950s, a few years later, Frank Young and C.N. Young, I mean, you know that C.N. Young and T.D. Lee, they are two students, very bright students. They went to US for PhD. And by the way, though, I mean, this is something I heard from one of the senior physicists many years ago when I was probably your age, Pasha Kabir. I mean, I don't remember where I heard this story, but he was a postdoc. He was Bethe's student, and he was a postdoc together with Weinberg and Feinberg in that group. So, so he told us that no, in what context I'm telling you this thing. I mean, I'll come back to that. I mean, I missed the thread in which context I'm telling you. I'll come back to that. But anyway, so this Young, so Young and Lee, so they didn't get the visa to go to US directly from China. Okay, after the war, so they had to go through India. So they had from China they came to Calcutta. From Calcutta they went to Bombay, and from Bombay they took the ship. So Young had malaria in Calcutta and spent 1 month there. And so one of the things they had to go through India. Saha wrote a letter to Fermi in support of their fellowship for the PhD student. They were going to Chicago at that time. So that's what I heard from Pasha Kabir. They had malaria. So I don't know. This is what I heard from Pasha Kabir. I mean, to what extent it is true or not, I didn't read it anywhere else. But this is an interesting story I shared with you on a lighter note. So Young in that was in 1954 or 55. He was visiting Barclay, and there Mills was there. Robert Mills was also visiting. So they shared an office and they started discussing about physics. So their goal was to generalize this QED. So it's for electron, no, it's electron and photon. So they were thinking about strong interaction, but to include strong interactions, you have to include both neutron as N and P, neutron and proton. So two objects. So for two objects, a single photon, or it's not just one electron. So you have to transform a column vector of two objects. So it's basically it's a doublet. So you need SU2 matrices. So you need higher groups, Lie groups. Okay. So they were playing with an arbitrary group. I mean, like not SU1. SU1 is U1. I mean, SU2, SU3, and so on. So for SUN, they did the same algebra. Okay. They were actually planning to explain strong interaction, but they found that of course, I mean, neutron and proton are one is charged, the other is neutral. So one there will be more photon like objects, and one will take neutron to proton, which means that is electrically charged, but necessarily they have to be massless, because that is the gauge invariance. But there is no such charged particle, charged object, spin 1 object which is massless. So it's mathematically beautiful, but realistically it's bogus. So that was their conclusion, but they didn't leave hope. I mean, something Young used to always think that if something is beautiful, it has to be correct. So he was just waiting. So they didn't throw this thing, I mean, but kept in mind. In the meantime, weak interaction was coming into the picture in a more kind of explicit and strong way, in the sense that people didn't believe about weak interaction before. Of course, radioactivity people have seen, but now people have started explaining, for example, why we get daylight, like sunlight, in the interior core of the sun. The strong interaction binds 4 protons together. It's a tight clump of 4 protons. Then it's weak interaction which convert 2 of the protons to neutrons, and then you get a helium, and then with some energy, and that photon sort of bounces back and forth inside the core of the sun, and 100,000 years later they come to the surface. 8 minutes later they come to you. So the role of weak interaction was getting increasingly more clear. And of course, beta decay was something that was remarkable, because I mean, I think Fermi was asked in his deathbed that what did you think to be the most interesting and special thing in your career, puzzling thing. Of course, he could have said many things, but he said beta decay. I said, why? Because electrons are coming from the nucleus. I mean, that is something that is puzzling. Electrons are in the outer shell. Why they are coming from inside the nucleus? So you don't think that you see that there have been relativity, general theory of relativity was also there, but Fermi didn't think how much stress they put on experimental discovery at that time. The electrons coming from the nucleus, and that couldn't be explained. Although Fermi tried to do it, but of course, I mean, he was also not satisfied with his theory. So, but eventually in 1957, weak interaction was kind of proved to be of V minus A nature, vector minus axial vector nature, and one of the former directors of this institute was involved. Sudarshan, with his supervisor Marshak, proposed this V minus A nature of weak interaction together with Feynman and Gell-Mann. And so people started thinking, okay, so if weak interaction is of vector minus axial vector, by the way, Salam also thought that it has to be V minus A, but Salam was always in contact with the experimentalists. So, he got some preliminary data, so never believe the preliminary data. So, the preliminary data suggested it is S minus T, the scalar minus tensor. So, Salam by that time submitted his paper to physical review, he withdrew it. Okay, so, V minus E paper he withdrew and he submitted S minus T paper. So, he missed the bus, but many people were doing. So, the data eventually turned out to be V minus A. Nobody got Nobel Prize for that, but the idea, some people were getting the idea that if weak interaction is of V minus A nature and electromagnetism is vectorial, right. So, there may be some connection. So, why not try to find a common source from where you are getting weak interaction and electromagnetism and some kind of a unification. So, around that time, I mean late 1950s and 59, 60, Sheldon Glashow, whose name I'll mention later, he joined for his PhD with Schwinger, and once, I mean, this is the beauty of having many stalwarts in your institute to give talks. So, Murray Gell-Mann visited Harvard at that time, and after his seminar, after some discussion, Murray Gell-Mann suggested Glashow, why don't you think about it, that how to unify electromagnetism with weak interaction. So, Glashow later said that, okay, I only thought about that issue for 2 years, and his PhD thesis was a paper marrying electromagnetism, that is SU2 cross U1 paper, without of course, the mass generation mechanism, where all the gauge bosons apart from photon will be massive. So, that was his PhD topic in 1962. Coming back to this V minus A nature, uh, it is clear that you can use one of those gauge boson, charged gauge boson, to explain beta decay, because neutron has to go to proton, and then so it is mediated by, today we know it is called W boson, some charged goes, but it has to be massive. I mean, otherwise nuclear, it will not be confined within the nuclear domain, right. But if you generate, if you give mass, then you are throwing the baby with the bath water. Essentially, your masslessness is an essential criteria of gauge invariance. So, how do you reconcile the masslessness that you need to have a consistent theory, and the demand that the photon like object, which is a charged object, has to be massive. I mean, this was a massive question. In fact, Young gave a seminar on V minus A, on beta decay. Essentially, beta decay he was trying to also explain, and Pauli was in US, and Pauli was in the front row. So, Pauli asked him, but what about the mass? He said that no, now we do not know anything. Actually, Young was giving a talk on Young-Mills theory, okay, and whether it can explain beta decay and so on. So, what about the mass? No, we do not know about it. Then Pauli dismissed it. I mean, then he, at some point of time, Young had to I mean, go back to his seat. He could not continue the talk. Suppose you ask me a question, fundamentally I can't answer, I have to sit down, I can't continue on the talk. That was the main point. I mean, that so then Oppenheimer said, let Frank proceed. I mean, then he could complete his talk. And then Pauli wrote him a letter that you made it impossible for me to talk to you. Pauli was absolutely nasty with him, but okay, I mean, you carry on, something like that. So, those were the time when you today, I mean, on a day all of us put arbitrary number of particles in our mathematical calculations with arbitrary charge and say that let it be experimentally tested. In those days it was very difficult unless it is already I mean it has a convincing reason to exist. I mean, so the question was how to generate the mass without losing the thing that we gained, that we tamed the infinity by having a massless particle which follows the gauge principle, but now realistically we have to generate the mass. That was a massive question. Okay, you got it. More or less parallelly, people were discussing about some other thing apparently unrelated, but they would be related in a big way. The role of symmetry. Okay, now it is important to study it because they realized that the this big question, well, it was not, it was there was no mathematical proof, but people had this kind of a eerie feeling that maybe it is a holy grail, that at the end of the day we would be able to join two problems. They are independent I will come to this problem, to two problems, whether they can together they can give you a solution. That is the reason I am talking about this idea. See that you think about let me tell you, I mean there is a symmetry on this dinner table, that if you sit there you can choose your glass either on the left or on the right, there is a symmetry, right. Now the moment any one of you chooses the glass on the right, then all of you will have to choose the glass on the right and vice versa. The symmetry is broken the moment you take a decision and choose on the right. Okay. Think about, so the symmetry is broken. Now think about water molecules in normal temperature. It has a perfect three-dimensional symmetry of the water molecules, but you go to sub-zero, you will get snowflakes. For example, this snowflake has I mean has a symmetry that if you rotate it by 60 degree you get the same flake. It is a discrete symmetry. So, it is lesser symmetry, it is not, it is less than the three-dimensional rotational symmetry. So, if your experience is limited to sub-zero temperature, you will not know that water molecules have a three-dimensional symmetry. You will see the flakes and you will conclude that it has only discrete symmetry, which in this case is rotation by 60 degree and so on. It could have been a different shape as well. So, we say that the symmetry is spontaneously broken. Okay, okay, what do I mean by, I will slowly explain what do I mean by that. Spontaneous symmetry is hidden in the sense that you are looking at a particular solution in a sub-zero temperature, you do not know the full symmetry, you do not know how, what are the laws of that govern the motion of the molecules, water molecules. The laws that govern the motion of the water molecules have a full three-dimensional symmetry, but in a particular phase which is the solid phase, you see a lesser symmetry. Okay. So, the question is that sometimes by looking at the solution you should not judge the symmetry of the equation of motion or of the system that governs the motion of the particles. I will give you another example like ferromagnetism. No, the magnets are aligned, okay, but around the critical temperature the higher symmetry goes to a lower symmetry when they are all aligned, right. I mean the tiny magnets, they are all aligned in one particular direction. So, if your experience is limited to that phase, you see lesser symmetry, but if your experience but it is pure electromagnetism which does not have any sense of direction, right. Now, I will give another example. It is not necessarily confined to subatomic zone. Okay. In classical physics way back in mid 1600, a French well, I mean polymath, I would say, his name is Boulouardis, and Robert Hooke, who was contemporary of Newton, they all anticipated this inverse squared law. Okay. But what they did not but they couldn't convincingly say that it is valid also for planetary motion. Why? Because Kepler's laws of planetary motion tell us that the orbit is elliptical, right? But if it is a inverse squared law, it is a radial thing, why it is not spherical? Okay, it should be perfectly spherical if it depends only on the distance and it is 1 over r square. What Newton conceived is that these planets have initial velocities. So, their elliptical orbit is not in contradiction to the inverse square law, which is perfectly symmetric. So, which means by looking at the solution, which is the elliptical orbit, you do not try to gauge the symmetry of the equation of motion. So, symmetry was spontaneously broken in the solution. The similar thing happens in superconductivity. Okay. I am slowly coming to the point where I will discuss about the generation of the mass. So, in superconductivity what happens? Okay. So, let me tell you that if you drive through a tunnel, for example, okay, the tunnel has lot of metal, no, on the wall. So, you see that your radio signal is disturbed, okay. But if you have a compass, the magnetic needle, that still points to the north. So, essentially a conductor, uh, it expels electric field, but is opaque to it does not do anything to the magnetic field. But in a superconductor, both electric fields and magnetic fields are driven out. Okay. So, I mean, since photon is a carrier of electromagnetism, it can penetrate only a thin layer of a superconducting surface, and so it appears to you that it has a short range interaction, because it does not go inside because of the Meissner effect. So, it appears to be massive inside the superconductor. So, superconductivity gives you a handle to try to understand that a photon might become massive because it has a short range interaction, that is the indication. So, what exactly happens that suppose an electron is coming to a lattice of ionized atoms, okay. It passes through and it gets attracted, because of the charge of the atoms, ionization charge. When the second electron comes, it sees a distorted lattice. So, inside the superconductor, if the two electrons come what is called closer to Fermi surface, I mean, so they act collectively. I mean, they attract each other magnetically, so that a combined object of two electrons very close to what is called the Fermi surface, they cancel their magnetism and become an object which is like a pair of two electrons called the Cooper pair, which does not have an intrinsic spin. Okay. So, the symmetry is spontaneously broken. So, what exactly is spontaneously broken? I mean, think of a two dimensional vector with the real part and imaginary part of the electron field. In electron field, it is basically the operator that destroys an electron in quantum field theory. So, the real part and imaginary part make a two dimensional surface. A 2D rotational symmetry was there in the beginning, and once Cooper pair is formed, what is left is a discrete symmetry, which is a rotation by 180 degree, which basically means E to minus E. So, that means that even number of E's can make a pair. Okay. So, very important thing is the original symmetry and the residual symmetry. So, in fact, BCS paper discusses about the approximation that if the two electrons are very close to Fermi surface, okay, some very close to each other, then they form the Cooper pair, and with that approximation you can actually calculate zero electrical resistance expelling the magnetic field Meissner effect. So, if you talk to a a field theorist like Weinberg, he would say, well, now we have to meet him somewhere else. He would say, no, I do not want to use that explanation to explain the exact properties of zero electrical resistance. It is not close to zero electrical resistance and total expelling of the magnetic field like Meissner effect by some approximate thing. I would use a symmetry. So, the symmetry and the residual, the remnant symmetry is very important. With that, I told you the symmetry is a two dimensional rotation in the real and imaginary plane of the electron field, and the residual symmetry is 180-degree rotation after spontaneous breaking of what is spontaneously broken is electromagnetism, and it appears that photon is massive. Okay. So, then Anderson conjectured that so these two things that that how would photon become massive, something is lost. What is lost is when symmetry is spontaneously broken, then a massless spin zero object will come out from the mathematics. So, Anderson conjectured, but we do not see that. There is no there is no mathematical proof at that time of when Anderson was doing it, for a reason. There cannot be any mathematical proof for that. He was thinking about it, that some kind of cancellation mechanism is there. So, photon appears very massive. Now, Nambu thought that okay, this is a good idea. So, why not think the universe to be a superconductor? And what happens when the Cooper pair breaks? Okay, it liberates energy, and the two electrons have more energy than before inside, because the binding energy is shared by the two electrons, and since energy is equivalent to mass, so those electrons appear massive. Okay. So, Nambu had the idea that let the universe be considered to be a superconductor. So, originally the nucleons are massless. So, so then after breaking of some symmetry, well, he actually conjectured that it is called chirality means hand, some symmetry which has to do with the handedness, I mean, okay, some kind of a global symmetry. The when it is spontaneously broken, the nucleons become massive. Okay. So, that was in the late 1950s, early 1960s, and Nambu said that, and based on Nambu's paper, Goldstone gave a solid mathematical proof that whenever a global, it has to be global continuous symmetry, not discrete symmetry, is spontaneously broken, there would be massless spin zero objects. You cannot bypass that, and the number of such objects depend on how many how the symmetry is broken. Okay. So, he gave a mathematical proof. So, those bosons were were called the Nambu Goldstone bosons. Nambu conjectured it only in the case of chiral symmetry, but Goldstone gave a detailed explanation. Then Nambu and Jonah Lesegino, they wrote a paper that in superconductivity, well, without much mathematical proof, there is no massless spin zero object. So, it must have been absorbed by the photon, and so photon appears massive inside a superconductor. Okay. So, I mean, what turned out to be a problem, that you do not see any massless spin zero object, and there is problem number 1, and problem number 2 is that you require massive spin 1 object. So, the question was how to reconcile the two. I mean, those two problems are independent problems, or think of it as in a unified way, one is a solution to the other. That was the attempt that people started doing at that time. So, In the next slide, I mean, is that I have some mathematical formula, but that's the only mathematical formula I have here, that if you for example move along this orbit, you don't it doesn't cost any energy, and that is the oscillation of this massless particle. Okay, so the massless particles move around this orbit, and uh, they are in the exponential of the original scalar field, and there is another spin zero object which is an excitation in the radial direction, just allow from that radius. If you consider that excitation, the radius in that plane is v. Okay, it is a constant mass dimensional parameter, and this radial excitation is what is this Goldstone's other boson. I mean, that is what would turn out to be the Higgs boson eventually. So, remember this, and this is the only mathematical formula I have in this theory. So I told you that what did Anderson, how much time will you give me? Okay, huh? Okay. So, what did Anderson tell us? That in the superconductor, somehow the so called massless spin zero object, I mean this number Goldstone boson is missing, and photon appears massive, and some kind of a cancellation mechanism is there. It is a conjecture without any mathematical proof. Okay. So, then this Klein, Oscar Klein and Bentley, it is not T. D. Lee, Bentley, they said no, superconductor is it is a non-relativistic system, it is a finite system, you cannot use special relativity there. So, there it is okay. I mean, they gave a proof that in a non-relativistic system you do not get any Goldstone boson. Okay. And then there was a guy whose name is Walter Gilbert. Uh, he started his PhD with Nick Kemmer in Imperial College, and Nick Kemmer was the PhD supervisor of Salam, but somehow Salam sort of captured him, and Gilbert started working with Salam, but he was more or less independent. So, Gilbert uh, uh, gave a proof that what Lee and Klein said, that it is so in a non-relativistic system you do not expect any massless particle spin zero object, but this idea can be this argument can be advanced also for a relativistic system. So, Gilbert said no, he gave a formal proof that no, in a relativistic theory, if global symmetry is spontaneously broken, you cannot bypass a spin zero. The spin zero object, spin zero massless object has to be there, but in nature there is no such thing. So, it is an impasse, I mean it is a roadblock. Okay. So, Gilbert by that time got disinterested in continuing in particle physics. So, on the same, so he went to Harvard, and he met Watson and Crick in the same corridor where his office was, and he got interested in DNA and in the molecular structure and the helical structure of DNA and so on. And in 1980 he got Nobel Prize for his work on DNA in chemistry or in life science chemistry, and he was also famous because he started this human genome project. But Gilbert's paper in particle physics, that was his last paper in particle physics, that launched Peter Higgs. So, Peter Higgs, so Gilbert went from particle physics to biophysics. Peter Higgs started his he did his PhD in biophysics, okay, molecular aspects, and he came to he came to Cambridge at that time, and he was probably a visitor or I do not know, postdoc or whatever, and he went to Imperial, he met Salam, he started discussing, and they went to Scottish summer school, and where he got this idea, because there you met his you meet all the other people thinking along the same direction. He got interested in particle physics, and he was very curious whether I can beat Guralnik in the argument, because Guralnik's argument didn't have any loophole. So, you have to have massless spin 0 object, no way you can escape that. Okay. So, he was thinking about it. At the same time, I will come to what Higgs did a little later before I give another example. So, Higgs was thinking how to bypass Guralnik, Gilbert. At the same time, in Imperial College, no, not in Imperial College, uh, mm, an American physicist, his name is Braut, he got a Belgian postdoc, his name is Angler, and both of them were interested in Kant's matter physics. So, they were thinking about again the symmetry breaking, but symmetry breaking in the spin chain. Okay. So, suppose you have the spins perfectly aligned, but they also precise, no, there is a spin. So, you can think of nearest neighbor interaction, and the way there is a periodic motion of the of the pattern in which the tips are moving, you can see some periodicity. So, actually in the context of spin waves, you can consider that to be the Goldstone mode, the mass less mode. Okay. So, it is a nearest neighbor interaction, if you think of. So, it is the infinitely long wave, I mean that would be your Goldstone mode. But then if you go beyond your assumption, initial assumption, it is a nearest neighbor, you start taking interaction of the next to nearest neighbor and so on, okay, it will be so random that the Goldstone mode would disappear. Okay. So, they got this idea that if you think of long range force, which means you are not confined to nearest neighbor interactions with all the particles, all the spins in your neighborhood and beyond, which is a long range interaction, then the Goldstone mode disappears. So, is it in electromagnetism the Goldstone mode? Electromagnetism is a long range force. So, can I apply that to electromagnetism, that the Goldstone mode would disappear, and we see what happens to the photon? Okay. So, where does the degree of freedom go? That is the question. Okay. So, then they wrote that paper in sometime in the early months of 1966, that if there is a photon and there is a symmetry breaking, then the photon becomes massive and the Goldstone boson disappears. There is a cannibalism, means the photon absorbs the Goldstone boson and becomes massive. Okay. A few months, okay, so Higgs went to that summer school, and somehow he got the idea, I mean he later claimed he got the idea there, that the same thing, that absolutely the same thing, that the mass generation mechanism is solved, Gilbert's argument can be bypassed. That Gilbert did not say that what happens in a gauge theory. Gilbert's argument is correct, if there is a global symmetry breaking, you cannot bypass the Goldstone mode. But if it is a gauge theory, in a gauge environment, it is possible that the photon becomes massive. So, he did the mathematical calculation exactly like Braut and Engler, and the Goldstone boson disappears and the cannibalism works and the photon becomes massive. He sent his paper to physical review letters, no, to physics letters B, or in those days probably physics letters, there was no A and B, and it got outrightly rejected. Okay. He was at visiting CERN, and if you are at CERN in those days, you have to send your paper to an European journal. So, paper got rejected. So, he got dejected, he sent the paper to physical review letter. In the physical review letter, the referee said that everything is fine, but what happens to, I showed you that sigma, the radial mode of excitation around, what happens to that mode? Nobody was interested in that mode. That's nobody was interested, because the mass generation is the most crucial issue, how to save, renormalize, how to save the invariance, gauge invariance and so on. Nobody cared about what happens to that, object which has whose coupling is unknown. Well, I mean, it's parameterized only, nobody cared. So, but this referee, I mean, allegedly Nambu, insisted that you write something about the properties of that particle. So, he wrote a few lines on that radial excitation. That makes him different from Brout and Angler. And Higgs was also not involved, I mean, not interested in that radial excitation. That would be the Higgs boson. Okay. Now, a few months later, uh, three people in the Imperial College, Guralnik, Hagen and Tom Kibble, they were also thinking about the same direction. They received the preprints of Higgs as well as of Brout and Englert, and they did not take it. Kibble later said he did not take it seriously, because the logics were not very tight. There was not much discussion on the degrees of freedom. So, they were trying to give a more robust proof of the same thing. Within 3 months, they wrote their paper, which is the best paper, because it has logically the most consistent and which takes into account the degrees of freedom, what happens to the degrees of freedom, but it is the same thing, it is the cannibalism paper for a photon, for how photon becomes massive, but no discussion on the radial excitation. Only Higgs was forced to write about it by the referee. Okay. So, these three. So, later on they regretted why, for learning it in a much better way and writing the paper in a more systematic and concise way, they wasted 3 months. Okay. So, again, I mean, one more thing I should mention, that still it was not a proof that the theory is renormalizable. I will mention a few lines on that. Okay. So, the radial excitation exists. On the same corridor, Guralnik, Hagen and Kibble were working. Salam and his collaborator John Ward were working on marrying weak interaction with electromagnetism, something similar to what Glashow had done in 1962, but this is 1965, 1966. Okay. So, Salam was and Ward were world experts of renormalization. So, they knew very well, I mean, Salam actually did not take Glassow's paper seriously, and he never, I mean, once he categorized some people to some level, he never, I mean, changed his opinion about that person. So, he never read Glassow's paper after that, and he regretted. So, again, they were working on SU2 cross U1, the right model to marry electromagnetism with weak interaction, so that you get the photon as well as the neutral object. That was again an embarrassment. Where is that neutral Z boson? Eventually that would be found to be a reality, but it is a photon like neutral object. I mean, what was the necessity? At least with W you can explain beta decay, with Z what you will do? They were embarrassed, but still they had this. But and at the same time, Guralnik and Hagen had no clue what is, how to marry weak interaction with electromagnetism. If they have talked, I mean, Imperial College had all the ingredients at that time. Okay. So, in 19 well, I am in which page? Yes. So, I mean, so Glashow wrote that SU2 cross U1 paper. Salam and Ward wrote that paper on marrying weak interaction with electromagnetism, but did not talk about the mass generation. They said that it's a problem still. Well, I mean, as I said, I mean, group theory was very well explained by Kibble and so on. So, then in 1967, Weinberg wrote the first paper having all the three things: how to marry weak interaction with electromagnetism, which is SU2 cross U1, and how to incorporate the idea of Higgs mechanism, I mean the mechanism of mass generation. So, that it was the first paper on what is called the standard model today, right. But Salam never wrote a paper. he gave a series of lectures. By that time, they realized, you see that they realized that it is going to be important. So, Salam gave a series of talks attended by some people who later said that, so there is a preprint of those talks later on, not at that time. It was some kind of a set of lectures on SU2 cross U1 theory with the mass generation mechanism. So, when it came to Nobel Prize eventually, okay, so so of course, I mean Glasgow, Salam, Weinberg, they got it because it's SU2 cross U1 theory for this thing. For the Higgs boson, of course, Higgs has to get it, right, because it's only Higgs who talked about that radial excitation that will turn out to be the Higgs boson. But what about the others? The Brout died in 2011, 2012 it was discovered. So, he is out, died 1 year before that. Angler, of course, Angler was included, but then it is a rule of 3. So, then from Hagen, Kibble and Guralnik, you have to choose one that is impossible. So, those two, maybe the third could have gone to Lean Evans, who constructed the LHC accelerator, but that was not given. Okay. So, the mechanism of mass, but Higgs said that it's, I mean Higgs did not say that, well, I was, although it was known as the Higgs boson, he used to feel embarrassed. He still feels embarrassed. He's still alive, right? Yeah. He still, yeah. He's gone, no? I mean this year, yeah. He used to feel embarrassed that, I mean, why it is called the Higgs boson, but anyway, and so much money has been spent for that I know 10,000, 10 billion euro and so on. So essentially the mechanism, the mass generation mechanism is, you can call it, I wrote it somewhere, you can say, yeah. So, this is the mass generation mechanism. Anderson, Brout, Angler, Guralnik, Hagen, Higgs, Kibble and 't Hooft. Now, let me tell you what 't Hooft did. 't Hooft, see, it was not yet proved that this SU2 cross U1 theory is sustainable at all energy scales. It has to be what is called renormalizable theory. Okay. Now, so Salam had the idea that somehow electromagnetism and gravity put together will make weak interaction and strong interaction together, it will be renormalizable. It was a vague idea, never wrote a paper on that. T.D. Lee also wrote a paper bringing in some hypothetical particles, how to make it renormalizable, but 't Hooft went to Karze's summer school. Well, I am advocating for many years summer schools because you may meet future Nobel laureates, you may get Nobel Prize for that as well. So, 't Hooft, and then Lee was giving a set of lectures on pion physics. See, why a pion scattering, you know about this Frossa bound, I mean the cross section has to saturate somehow, right. So, pions are very similar to the formula I have written, no. The exponential, there are pions which are the Goldstone bosons, and the sigmas are what I wrote sigma in the radial excitation, they called Higgs. So, when you consider pion pi scattering, I mean he had the idea that it has to be mediated, no sorry, Ben Lee gave a talk, Ben Lee gave a set of lectures that it becomes, it is not renormalizable of course, but it becomes a I mean kind of tractable theory even at high energy. The cross section doesn't, cross section saturates, only that it does not have any abnormal growth, only if you consider this pi mediated by sigma and then to pi scattering. So, pi scattering mediated by sigma. So, then 't Hooft got the idea that for WW scattering, when you consider WW scattering, the cross section, it has a 4W vertex that has a E4 kind of divergence, energy to the fourth, but then it gets cancelled if you consider other diagrams mediated by other WWZ and so on, but it still has that E square divergence. Okay. So, only if you consider the intermediate radial excitation, what is this unwanted object that Higgs was forced to put because of Referee's insistence, if you put that as an intermediate mediator, he had that idea that maybe it is the clue like the sigma field in pion physics. So, he came back and he told his supervisor Tini Weltman that I will try this, but they needed some kind of a computer program, and Weltman wrote Spoonsip. That was one of the first computer programs on particle physics. So that had to be run at CERN only. So he flew to CERN, run that program, and then there was a factor of 4 missing, and this way that symmetry factor they settled it, and then, oh yes, my theory is renormalizable. The proof is much more complicated because Etoft early 71 or 72 he wrote his paper based on path integral formalism. Nobody knew path integral at that, although Feynman developed it. So formalism, nobody used it in particle physics at that time. So in 1972 there was a Rochester conference in Amsterdam. So in the backdrop of that conference, Weltman organized some kind of a parallel session, gave 1 hour to settle this issue. He wanted to launch Etoft, but Etoft means, although also he was a co-author at the same time of that paper, and he invited T.D. Lee, Sidney Coleman, and Salam to that room to and Salam gave a lecture which I mean kind of, it was known that it is clumsy. T.D. Lee gave his own idea about normalizability that also had to incorporate many things. Weinberg was also there, and then Etoft, who was a PhD student at that time, gave his lecture. Okay, nobody understood because it was in path integral, but these people had this feeling that it is really important. Yes, 5 minutes. Yes, yes, yeah. So it turned out that because of Etoft's paper, standard model got the respect that it deserved eventually. In fact, neither Salam nor Weinberg after 1967 wrote a paper on SU2 cross U1 theory for the next 4 or 5 years. They moved to strong interaction. They didn't realize that this paper is going to be important. Only after Etoft's paper they came back and started working vociferously on it. So again in 2012, that is what Indu mentioned, when the Higgs boson was discovered, it was found to decay into 2 photons among many channels that who mentioned it? I mean, you mentioned it, Kajuridi mentioned about the branching ratio, but the fact that, see, experimentalists do not care about your theory. So the fact that it is decaying into 2 photons implies that it has a spin 0 object. I mean, because a spin 1 object cannot decay into 2, a massive spin 1 object cannot decay into 2 massless spin 1 objects, Young's theorem. This is angular momentum conservation. So the spin 0 nature of the discovered particle was established at that time. Then from the angular momentum conservation, well, I mean study of angular momentum and other things also established it is a spin 0 object. The parity was kind of established. Well, I mean there is still some room of that it is pseudo scalar experimentally speaking, but the chances are very small. It is a scalar particle, and this is the first time that if it is an elementary object, most likely it is, although the scope that it is a composite object is still there, but it is more likely to be elementary than composite. So the first time you are seeing the Yukawa force, which is not quantized. Previously you have seen gauge force which is quantized and so on. So you can see that this is Higgs 2012, Onglayer and Rolf Feuer, the CERN Director General, celebrating, and this is the pic when Joe Intandela, right? I mean that was the CMS spokesperson, I mean showed it, our heart stopped. I mean that is the Higgs boson, people have been looking for it, and you can see he mentioned at that time that so much money has been spent on it, feel embarrassed. Okay, so then well, I mean let me tell you, I mean that the story, the standard model particle content, whatever was proposed is now discovered. Okay, but as Rick mentioned that, I mean we are still perplexed why the Higgs is light, in spite of the fact is more than 100 times heavier than the proton, but still it does not have any intrinsic sense of direction, it does not have a spin, it does not have any angular. So for a point particle which has no intrinsic sense of direction, again as I said, I mean it can eat up infinite amount of energy by eating its own tail in a various kinds of loops, and it the mass will, and energy is mass, so mass will shoot up to infinity, but it is 100 GeV, why it is not? So that thing is still an open domain. And one of the things that I mean 10 even 10 15 years back, in each such conference 95% of the talks used to be on supersymmetry. Now these days only 5% talks are in supersymmetry. The rating has fallen. The share market on supersymmetry is, but it turned actually supersymmetry is a very elegant and mathematically consistent theory. I mean, so people thought that it, still many people think that the symmetry is there, but it's broken in such a way that it is just beyond the boundary of our of our access through the accelerators. So people think about additional dimensions like it's a curled, so that a pencil, for example, I mean you will see it as a line. So this from a distance. So if you come closer, means if you go to higher energy, you can unravel that higher dimension. Or supersymmetry is also kind of a higher dimension. I mean you can think of, you go to your imaginary dimension. Okay. So in the sense that, I mean in real world you don't, so you think that you are in some kind of this 3 plus 1 dimension plus some imaginary dimension, which may be a fifth dimension, fourth, fifth, sixth dimension, or some kind of supersymmetry which is also a fermionic direction. Okay. This is also extra dimension. Okay. So that can give you a solution to why the Higgs mass is 100 GeV. Let me tell you, I mean why I call supersymmetry to be an additional dimension. It is a symmetry between fermions and boson. It means that for every fermion there is a boson and vice versa. But you can think it in this way, that think of taking a square root of something impossible, well I mean some impossible square root, like square root of -1. Okay. So 400 years back somebody took the square root of -1 and said that this is the imaginary thing, right. This is a square, is something impossible apparently, I mean conceptually, square root of -1, but it opened up a new dimension, right. I mean you can put your plot in the real axis and the imaginary axis. So taking square root of -1 gave you an additional dimension to sort of I mean represent your thought process. So if you take the square root of translation, for example, translation, like translation, rotation, these are the operators. So if you take the square root of translation, you get an additional dimension which is the fermionic direction, and supersymmetry, superspace, the additional, when I am talking about additional dimension, it is that direction that is going to give you supersymmetry, square root of translation. Okay. But how do you represent it? Like when you represent the imaginary axis, you still represent through real number 1, 2, 3, 4, 5, and in the imaginary axis a plus ib kind of thing. But if you try to represent things in super space, you cannot use real numbers, like well, by real I do not mean the real and imaginary sense, the numbers that 1, 2, 3, 4, 5, the way we know 1 cow, 2 cars, I mean it is not those numbers. Okay. For angular momentum, yes, 5 times this, 4 times that, for spin also 3 by 2, 1 by 2, whatever. But for super space you need to invoke certain numbers which are called Grassmann numbers. Okay. So let me give you an example, like take a number a, okay, a can be anything a, such that a square is 0, right. It is basically related to fermions. So 2 fermions, so square of a is 0, right. So take b, b square is also 0. Okay. Now suppose if they are ordinary numbers, a times b is b times a, right, 1 times 2 is 2 times 1 and so on, that is how we conceive the numbers. But if a square is 0 and b square is 0, and suppose addition works in the same way, like c is a plus b, then c square is also 0, c is also like, so then a plus b square is 0. So then a plus b square is a plus b times a plus b. So a square is 0, b square is 0. So then ab plus ba is 0, agreed. So ab is minus ba. So, these numbers, I gave you a very crude example, okay, but these numbers which do not commute but anti-commute are Grassmann number, their square is also 0. So, with that you can describe the a full symmetry, where in addition to the standard translation, rotation, you can also include some symmetry in that, you know in those spaces and in the mixed spaces as well. And then you will see that for every spin half particle there is a partner which is spin 1 and so on, and vice versa. Spin 0 has a spin half partner and so on. So, that is a full symmetry of particle and superparticles, but the symmetry is not there in nature, it is broken. Not only it is broken, it is very badly broken. So, that is the reason we have not seen it, that is the way, but we expected to see it, but yes, 2 minutes and I am done. Minus 2 minutes, yes. Okay, so and another thing, I assume that Higgs to be an elementary object, but it can be composed. There are many other things which can be different types of new physics that Rick had mentioned and Kajuri had constrained. So, with that note, I end, but I thought that I give you the some kind of it was a storytelling about how the last 100 years work finally yielded something which relied on the previous decades, always, all the way back to 1920, 1930s. Nothing is unrelated. Okay, thank you very much.